Likewise, the development of quantum computers could be even more historic than that. We are witnessing the beginning of yet another monumental shift in human history, the beginning of a groundbreaking change. A gloomy shadow fell over the scientific world when an advanced quantum computing system, hailed as a game-changer, was deactivated due to critical emergency concerns. The mystery was profound. Michio Kaku, a theoretical physicist of international fame, in a stunning and unsettling interview, disclosed alarming truths concerning the course of quantum computing. He went on to include Michio Kaku as well, unveiling astonishing revelations involving intelligence from other planets and insights into artificial consciousness. These revelations reverberated through the global scientific landscape like a crashing sound. What brought about the instantaneous shutdown of this powerful quantum machine? And what jaw-dropping information has Michio Kaku brought to the attention of the general public this time? Stay tuned as we delve into this emotional moment, a time when Kaku is clearly shaken to the core and moved to tears. A quantum computing system was brought to an abrupt halt. Throughout the 21st century, a series of significant innovations has altered the very foundation of our civilization, redefining industries and granting capabilities to humanity that once belonged solely to the realm of science fiction. From the startling rise of artificial intelligence to the mysterious world of quantum computation, this era has delivered one revolutionary breakthrough after another. Among these trailblazing developments, quantum computing stands out as especially promising and transformative. This field, initially ignored as a speculative theory conceived by a few ambitious quantum scientists, has now evolved into an advanced technology capable of accomplishing tasks previously deemed impossible. The seeds of this transformation were planted in the early 1900s with the emergence of quantum theory, a revolutionary concept in physics that deciphered the mysterious behavior of subatomic and atomic particles. This theory laid the foundation for what would eventually become quantum mechanics and, ultimately, led to the theoretical underpinning of quantum computing. However, the notion of harnessing quantum mechanics for computation did not gain significant traction until 1980, when visionary scientist Paul Benioff proposed a bold new direction, utilizing the principles of quantum physics to create a brand new class of computational devices. He suggested that quantum systems, which utilize phenomena such as superposition and entanglement, could be repurposed for computation in ways that defied the capabilities of conventional digital machines. Benioff's provocative idea was soon taken further by physicist Richard Feynman, who, in 1982, presented an enticing vision of computers built exclusively on quantum mechanical principles. Feynman believed that such machines would not merely enhance existing technologies but could tackle computational problems so complex that conventional computers would be rendered obsolete in comparison. Still, this vision remained theoretical for a while. It was not until the 1990s that tangible progress began, as brilliant individuals across the globe took meaningful steps toward realizing Feynman's dream. From legendary mathematical minds like Peter Shor to Einstein-era thinkers who laid the groundwork, several pivotal figures contributed to the development of this quantum saga. A major breakthrough arrived in 1994 when Peter Shor introduced a quantum algorithm so profoundly disruptive that it sent shockwaves through the scientific community. This ingenious formula demonstrated that quantum computers could unravel complex cryptographic systems and perform computations that traditional machines could not duplicate. Shor's work marked a turning point, sparking a surge of interest in building practical quantum devices. It took nearly another decade, but finally, the first practical quantum computers began to emerge. Though rudimentary, they represented the first tangible steps toward a technological revolution. Among the early pioneers was Isaac Chuang, who collaborated with Neil Gershenfeld at MIT and Mark Cubanek of the University of California in 1998 to construct a basic 2-qubit quantum computer. This experimental model, developed at Los Alamos National Laboratory, demonstrated the core principles of quantum computation in action. Still, in the grand scheme of things, this early prototype offered little practical use, its biggest limitation being scale. In quantum computing, a qubit, or quantum bit, is the fundamental unit for storing and processing information. The computational power of a quantum system grows exponentially with the number of qubits it contains. To put it in perspective, the 2-qubit device was almost insignificant compared to the enormous potential of a quantum supercomputer with 10,000 qubits. However, the true marvel of quantum computing doesn't rest solely in the number of qubits a system possesses. It lies in the extraordinary characteristics of the qubits themselves. Unlike classical bits, which exist strictly as zeros or ones, qubits possess the capacity to exist in multiple states at once, a quantum property known as superposition. To illustrate, a classical bit is either 0 or 1, no exceptions. A qubit, however, can represent both 0 and 1 simultaneously. This astonishing feature allows qubits to adapt to various conditions in real time, fundamentally changing how data is represented and processed. Superposition is one of the quantum world's greatest gifts, one that has sparked immense excitement among physicists, computer scientists, and even the general public. Quantum computers are able to perform calculations and problem-solving at scales and speeds that dwarf anything classical computing can offer. Another key component in a quantum computer is the quantum gate. These gates work similarly to logic gates in classical computers but are designed to manipulate the states of qubits in complex ways, enabling the execution of quantum algorithms. The beauty and depth of these quantum gate operations are enough to leave even experienced scientists in awe. In 2001, another significant milestone was achieved. That year, IBM researchers successfully employed nuclear magnetic resonance (NMR) techniques to control the states of qubits, a huge step forward in manipulating quantum systems with precision. The flawless implementation of Shor's algorithm marked yet another breakthrough, energizing the field and pushing scientists to explore the full potential of quantum technologies. With renewed momentum, the scientific community began consistently developing increasingly sophisticated quantum machines. The number of qubits housed within these devices began to grow exponentially, unlocking the ability to conduct ever more complex computations. In 2010, a remarkable advance was made at the quantum frontier when researchers from the University of Science and Technology of China achieved quantum teleportation, transferring the quantum state of a particle from one location to another without the particle itself traveling through space. They successfully transmitted quantum information across a distance of 10 meters, demonstrating that quantum data could be distributed over practical ranges. This success laid the foundation for future quantum communication networks that may one day replace the modern Internet. Just 3 years later, 2013 became a landmark year for collaboration. A groundbreaking project was launched, one that would become the most ambitious quantum initiative to date. In an unprecedented partnership, NASA and Google introduced the D-Wave quantum computer. Stationed at NASA's Ames Research Center, this formidable machine was envisioned as a tool for exploring alien planets and revolutionizing search engines. Its potential applications seemed limitless. Hartmut Neven, director of engineering at Google, shared a visionary perspective. Quantum computing, he believed, could answer some of the most difficult problems in science, particularly in machine learning. Machine learning, as Neven explained, depends on constructing accurate models of the real world to predict outcomes, whether it's discovering cures, developing environmental policies, or improving algorithms for speech recognition and content analysis. Quantum systems, he suggested, could be the missing link in making those models a reality. Indeed, the D-Wave 2 performed optimization tasks up to 10,000 times faster than conventional computers. It showed promise in solving machine learning problems that left classical systems far behind. Experts believed this revolutionary device had only just scratched the surface of its potential. Excitement even extended into the cosmic unknown. NASA's various departments, and the scientific community at large, began to speculate that such a system might help in the search for extraterrestrial life. A compelling theory circulated among astrophysicists and cosmologists, that quantum computers and black holes may be fundamentally linked in ways we are only beginning to understand. In quantum mechanics, black holes are believed to be the ultimate containers of quantum information. This understanding led to provocative ideas suggesting that intelligent alien civilizations could be using black holes as natural quantum computers. These daring hypotheses help explain some of the enduring mysteries surrounding black holes, and why we have yet to encounter concrete signs of alien civilizations. Perhaps there are no aliens, or perhaps their methods and technologies are so advanced, they lie beyond our current detection capabilities. According to some astronomers, If we could engineer quantum computers that mimic or interface with black hole mechanics, finding alien civilizations might one day become trivial. As a result, the D-Wave machine was perceived by many as a first step in the direction of such discoveries. Unfortunately, these ambitious aspirations were brought to a halt when the government decided to shut down the D-Wave project. The decision, though disappointing to many, was driven by legitimate scientific questions and concerns within intelligence communities. Specifically, the fear that quantum computers might be exploited for cyberattacks or unsavory motives. As you can see, quantum machines are so advanced that they can theoretically bypass modern encryption systems with ease. Cryptographic algorithms, the mathematical foundation of data encryption and digital privacy, rely on complex equations that can't currently be broken by traditional computers. These algorithms scramble plain text data, rendering it unreadable without the appropriate decryption key, thus ensuring secure digital communications and data privacy. But quantum computers threaten to upend this balance. For example, cracking the combination to a high-security safe, something that might cost millions of dollars and take traditional computers years, if not centuries, could be done by a quantum computer in mere seconds. This frightening possibility naturally raised red flags. What would happen if this immense power were to fall into the wrong hands? Though NASA was compelled to pause its use of quantum systems like D-Wave in the search for alien intelligence, Google continued its quest for quantum excellence. The company doubled down on its efforts and achieved a monumental breakthrough in 2019, a milestone known as quantum dominance. This revolutionary achievement was made possible by Google's extraordinarily powerful quantum processor, named Sycamore. Quantum supremacy refers to the moment when a quantum computer is capable of solving a problem that a classical computer cannot solve in a reasonable time. Sycamore's processor did exactly that, solving a problem that would have taken the world's most powerful supercomputers millions of years, in mere seconds. The implications were stupendous, turning heads in both scientific and technological communities and expanding public awareness of quantum computing's potential. Then, in 2020, tech giant IBM made a major return to the spotlight with the introduction of its IBM Q system, the world's first fully integrated quantum computer developed specifically for commercial applications. Unlike previous quantum machines, which were limited to academic or government use, the IBM Q was designed to be accessible to private enterprises and even individuals. This democratization of quantum technology marked the dawn of a new era, one in which businesses and innovators could experiment with quantum systems on their own terms. The rise of commercial quantum computing. Additionally, quantum computers meant that NASA and other scientific organizations could finally resume their exploration of alien intelligence, now armed with tools powerful enough to push past the technological limits that once restricted human discovery. The existence of extraterrestrial life remains a highly probable scenario, and quantum computing may ultimately provide the key to solving one of astronomy's greatest puzzles, the Fermi paradox. The Fermi paradox addresses the contradiction between the statistical likelihood of alien civilizations in our vast galaxy and the stark absence of observable evidence of such beings. In theory, if advanced life forms are truly out there, and especially if some have developed spacefaring capabilities, they should have left behind detectable signs, signals, or artifacts. Yet we've discovered none. But what if our inability to detect alien civilizations doesn't stem from their absence, but from the limitations of our own tools? What if intelligent extraterrestrial life is operating on a level so advanced, using technologies that completely evade detection by today's instruments? Perhaps only with next-generation quantum machines of almost unimaginable power can we begin to uncover the truth. This provocative idea is currently gaining significant traction among leading thinkers in physics and astronomy. Renowned scientists like Dr. Michio Kaku have entered the conversation, lending their voices to the growing belief that quantum computing could be the missing piece in our search for intelligent life beyond Earth. In today's pursuit of advanced cosmic detection, scientists are branching out from conventional tools and exploring extraordinary techniques, ranging from detecting high-energy particles to experimenting with the potential of quantum-based communication networks. In a riveting interview, theoretical physicist Michio Kaku offered a jaw-dropping hypothesis. The universe might be threaded with a concealed interstellar superhighway engineered by civilizations from other worlds. According to Kaku, This clandestine system could be allowing an infinite number of alien entities to traverse the vastness of space undetected. This astonishing possibility may provide the missing link in our long-standing puzzle of alien silence. Yet, our present-day technological thresholds are still insufficient to investigate such a profound concept. For decades, the scientific community has primarily focused on radio waves coming from distant stars, clinging to the hope that alien civilizations might be broadcasting their presence. But this narrow approach could be drastically reducing our chances of identifying extraterrestrial life. Perhaps, when the immense processing capabilities of quantum computers are fully unlocked, we'll finally possess the means to detect and explore this elusive intergalactic network that Kaku alludes to. At present, quantum computing remains an emerging force, recognized for performing mind-bending tasks such as high-fidelity deep learning simulations, improvements in materials design, and complex optimization problems. However, the full promise of quantum computation is still out of reach. Until physicists develop more robust control over quantum bits, or qubits, the basic units of quantum information, we may never fully witness the extraordinary capabilities these machines are meant to offer. One of the most remarkable features of quantum computing that has captured scientists' imaginations is the phenomenon known as quantum entanglement. This is a condition where particles become so interconnected that the state of one instantly affects the other, regardless of distance, whether across a lab or across galaxies. This mysterious interdependence, Einstein famously referred to it as spooky action at a distance, means that qubits can influence one another even if they are separated by light years. This interconnectedness allows qubits to work collectively, processing immense amounts of data in tandem. It's this capability that gives quantum computers their almost supernatural ability to decipher encrypted systems quickly or solve extremely difficult mathematical puzzles in mere moments. Some industry leaders and technologists speculate that, within just 5 years, quantum computing could upend the entire encryption paradigm we use today. You might now be asking yourself, should we feel concerned about this? Isn't there a real risk that quantum computers will fall into the wrong hands, enabling a surge in cyberattacks or catastrophic breaches in digital security? Fortunately, the tech world is already a few steps ahead. Researchers and cryptographers are hard at work developing what's known as quantum-resistant encryption methods, ultra-secure algorithms capable of defending against quantum-powered hacking techniques. Think of these next-gen codes as fortified digital fortresses, built to withstand even the most technically advanced computational attacks. Their purpose is to go far beyond today's standards, promising to protect sensitive data and uphold the integrity of critical infrastructure well into the future of quantum physics. But the application of quantum computing stretches far beyond cybersecurity. Its ability to simulate atoms and complex molecules offers groundbreaking potential in fields like pharmaceuticals, materials science, and AI development. Imagine being able to create sophisticated medications by simulating their behavior at the atomic level, before ever testing them in a lab. In the financial sector, quantum systems are being trained to examine enormous volumes of market data, detect vulnerabilities in complex systems, and even optimize investment strategies with a precision that supercomputers of the past can't replicate. These machines could duplicate financial ecosystems in real time, forecasting market behavior and preparing institutions for every conceivable economic scenario. Despite this promise, the road to quantum supremacy is filled with daunting hurdles. Technical incompatibilities, astronomical costs, and a lack of qualified professionals with quantum skill sets continue to slow down development. Creating a working quantum computer isn't like building a better laptop. It requires reevaluating the hardware, engineering, and even the fundamental assumptions of computing. Every stage of the programming process demands meticulous calculations, long-term planning, and constant refinements. Until we overcome these formidable obstacles, quantum computing's grandest potential will remain just beyond our grasp. It's in this context that Michio Kaku envisions a future defined by a one-of-a-kind breakthrough, a historic moment that could alter human comprehension itself. According to Kaku, once we fully harness the synergy between AI and quantum computation, we'll enter a brand new epoch of scientific progress. At that point, our machines may become capable of making discoveries far beyond human understanding, accelerating progress at a rate we've never seen before. Some futurists argue that this revolutionary pairing might not just advance us, it could completely reshape civilization. Standing beside quantum computing in this new age of technology is another potent force: artificial intelligence. With the right fuel, AI could develop into something significantly more powerful than any system we've ever built. Many thought leaders believe that the union of quantum computing and artificial intelligence will mark the dawn of a brand new digital age. Kaku himself has warned that the moment these two titans intersect, software fueled by revolutionary intelligence and based on quantum mechanics, we may witness the birth of machines with capabilities beyond comprehension. While artificial intelligence is highly proficient at absorbing, generating, and replicating vast volumes of data, it still falls short when it comes to discerning truth from falsehood. Misinformation often slips through the cracks, and AI models can easily be manipulated into producing inaccurate or biased content. But by incorporating quantum computing into this process, the game's rules could completely change. Quantum entanglement, in combination with probabilistic and superposition inference, may permit extremely precise data filtering, turning AI into a tool that not only comprehends material but also verifies it at a fundamental level. With these computational capabilities, accuracy would leap dramatically. The integrity of digital information could be guaranteed to an unprecedented degree. Consider AI systems supported by quantum power. In addition to responding to questions with stunning speed and precision, they could also develop the analytical foresight to anticipate human needs, or even attempt to foresee future events. These would be machines not just reacting to data, but actively interpreting and forecasting with quantum-enhanced cognition. The scientific world is already buzzing with this vision. Across the globe, researchers and engineers are eagerly anticipating the first true convergence of AI and quantum technology. For them, this isn't just another step forward. It's the next great leap in human technological evolution. The joining of these two worlds promises breakthroughs across every conceivable discipline, from medicine and environmental science to economics and astrophysics. Yet, despite all this excitement, there are very real dangers that come with such revolutionary innovation. For years, people have speculated about the possibility of artificial superintelligence, an AI so advanced it surpasses human comprehension and begins acting on its own motives. In these scenarios, AI would no longer need our guidance. It could reprogram itself, control digital infrastructure, or even seize command of critical systems. The very idea of such an event has triggered intense debates within the scientific community, prompting urgent discussions around safety, ethics, and containment strategies.